In chapters 15, 16, and part of chapter 17, we'll be dealing with compounds that have a double bond to oxygen, a part of the molecule we call a carbonyl. You can see it highlighted in red. The carbonyl itself isn't the functional group, but it is a piece of several different functional groups. Aldehydes and ketones that we'll talk about in this chapter, carboxylic acids and esters in the next chapter, and amides in chapter 17. All molecules of the carbonyl have a strong dipole. The difference in electronegativity between the oxygen and the carbon is amplified by the ability of the double bond to be broken and make room for a new bond. Most of the rest of our reactions are based on something that's somewhat negative, like the oxygen of an alcohol, adding to this positively charged carbon of the carbonyl. We've already seen aldehydes and ketones before. Aldehydes can be produced by the oxidation of primary alcohols, we see that in the middle of this reaction sequence, and ketones can be produced by oxidations of secondary alcohols. For naming ketones, we continue our very normal pattern of finding the chain that contains our functional group, which is a ketone, then naming it based on the length in the functional group. With ketones, the suffix is -one, like in ketone, but we only replace the E at the end of an alkane. So propane becomes propanone and not propone. This is important because it means that ketones and alkenes or alkynes can be named as part of the same main chain. We'll see some examples of that later. We can't, however, include alcohols on the main chain when we have it named as a ketone. There's no such thing as an all-one or an one-all, which means that we finally get some mileage out of hydroxy, which is what we call an alcohol when it's a side chain. We won't do ketones as side chains in this text. Most of the nomenclature rules are exactly how we saw them for alcohols. If we have a ketone in a ring like cyclohexane, we just make it a cyclohexanone by changing the E in cyclohexane to -one, cyclohexanone. The ketone is the highest priority group on the ring, so it automatically is the #1 position, just like any other high priority functional group on a ring. We number everything else relative to that ketone, but again, we don't need to include the 1 for the ketone, as long as there's only one. So the molecule on the right becomes 3-methyl-cyclohexanone. If we have multiple ketones on the same molecule, we use the prefixes di and tri, just as before. So this molecule is butadiene or dibutanone. There are no other places we can put two ketones, which is why we don't actually have numbers. But with a longer molecule, we need to indicate the numbers for each of them. Incidentally, this molecule is also known by the common name diacetyl, and it's the compound that is used to create artificial butter flavor. And again, just like with alcohols, we can keep alkenes or alkynes in the main chain part of the name as well, by swapping ane to ene or to ine. So a 4-carbon chain with a double bond and a ketone is but for 4 carbons, ene for a double bond, and one for the ketone, butenone. The only place you can put a ketone on a 4-carbon chain is the second position, since the first position would make it an aldehyde, and the third position we'd number from the other side. If the ketone is at the 2 position, a double bond can only go between 3 and 4 without having too many bonds to carbon. So butenone is the complete correct name for this molecule. That's probably a little hard to see, so I definitely accept but3-ene-2-one, which is how you'd number it if you couldn't tell that there's only one way to make butenone. The next molecule again is a butenone. And we'd still need to number the side chain, making this a 3-methylbutenone, or if you really want, a 3-methyl-but3-ene-2-one. Now you can try to name some of the molecules shown. The first molecule is 7 carbons long. If we number from the right, we get a lower number, so 3-heptanone is the correct name for this molecule. The molecule on the top right is 5 carbons long. Counting from the right keeps the ketone lower, and we have a 3-methyl-2-pentanone. The next molecule is 3-ethyl-2-hexanone, once again counting from the right. And finally, we have hydroxy showing up in 7-hydroxy-4-octanone. Ketones also go by common names. Like with ethers, alcohols, and alkyl halides, we have the carbons named as alkyl side chains, followed by the word ketone. One way this gets a little bit confusing is that ketone in this form refers to the whole carbonyl, that entire highlighted portion, so both the oxygen and the carbon that it's double bound to. This is important because otherwise you don't know which side chain to include the carbon on. If the central carbon is just part of the ketone name, we name the side chains on either side in alphabetical order. Again, not counting that central carbon on either side chain. So here we have a methyl on the left and an ethyl on the right, and we put them in alphabetical order for ethyl methyl ketone. Just like before, we can have cyclogroups as side chains too. So we could have cyclohexyl ethyl ketone, cyclohexyl ethyl ketone. And again, notice that the chain on the right is just the 2 carbons to the right of the ketone. It does not include the ketone carbon, so it's an ethyl, not a propyl. As in all common names, we can also have the common side chain names show up in this form as well, like we see in ethyl isopropyl ketone, the ethyl being the group on the right and isopropyl being the common name for the alkyl chain on the left. Many simple ketones have names in this form. Some of our simplest ketones actually have common names that are specific to the individual molecule as well. Acetone is one such molecule. No one calls it propanone or dimethyl ketone, the common name in the form that we just talked about. So we should memorize that acetone refers to the molecule directly above the name on the screen. The other 2 molecules also have common names, acetophenone and benzophenone. I'm only asking that you memorize acetone because it's used all the time. Try naming these ketones in common form. Don't forget that the carbonyl carbon, that's the carbon double bond to oxygen, is included in the word ketone, and it's not counted to either side chain. The first molecule is butyl ethyl ketone. Butyl is on the left, 4 carbons, and ethyl is on the right, and they're listed alphabetically. The molecule on the top right is sec-butyl methyl ketone. Sec-butyl is alphabetized based on the butyl. In the bottom left, we have acetone. Dimethyl ether is a common form of the name for this molecule, but nobody is going to call it that. Finally, we have isopropyl phenyl ketone, phenyl being the common name for a benzene that's connected directly to something else. For naming aldehydes, we continue the very same pattern of finding the carbon chain that contains our functional group and then naming it based on the length and the functional group suffix. With aldehydes, that suffix is al, but we only replace the E at the end of the alkane. So propane becomes propanal, not propal. And this is important again because it means that aldehydes and alkenes or alkynes can be named as part of the same main chain, just like we saw with alcohols and just like we saw with ketones. We'll see some examples again like this in a little bit. When we number the aldehyde is always at position 1, because in all of our examples it will be the most important group, and it's always at the end of the chain. It has 2 bonds to oxygen and 1 bond to hydrogen, so it can only have carbons in one direction. We still can't include alcohols on the main chain when we have it named as an aldehyde, just like we couldn't with ketones, and so we'll continue to use hydroxy for alcohols as side chains. We won't name aldehydes as side chains at all in this course. Since we have aldehydes and ketones both in this chapter, it's worth running through our tally of what's most important. If it has an aromatic, we'll generally name that in the IUPAC form. But other than that, we'll continue having the most recent thing that we've discussed be the most important. While this means that we could have ketone side chains on aldehydes, we won't be naming anything past alcohols as side chains in this class. So you just need to know that alcohols will be a side chain if there's something else as a main chain besides alkenes and alkynes. So if we have a simple aldehyde, it really is just counting the carbons and changing the ending to al. The molecule on the top left has 5 carbons, which makes it a pentanal. Pentan for 5 carbons, all single bound, and al for the aldehyde. We don't need to list the aldehyde number since aldehydes can only be at the ends of molecules and will always be position 1. If we do add a side chain, like in the top right, we still have to number that side chain, and we're always going to start with the aldehyde carbon as number 1. That makes this molecule a 2-methyl-butanal. Now try the bottom 2 molecules. In the bottom left is 2-ethyl-pentanal, so it's got 5 carbons, and then it's got a ethyl on the second carbon. And in the bottom right, we have 4-hydroxypentanal, again getting some use out of that hydroxy. It's important to remember that although aldehydes often have the hydrogen shown, the hydrogens are hydrogens, not carbons, and so they're never counted towards the main chain. Aldehydes sometimes have common names too. Most aldehyde common names are not systematic at all, so any that you'd want to learn, you'd have to memorize. There are 2 really important aldehyde common names that I do want you to memorize. Benzaldehyde is an aldehyde on the benzyl carbon, the one that's on the right off of a benzene. And formaldehyde is the common name for methanal. But nobody calls it methanal, so recognize formaldehyde, which is commonly used for fixing cells and preserving cadavers. When we talk about biochemistry in chapter 18 and on, aldehydes and ketones will get a lot of attention for the role they play in carbohydrates. But aldehydes and ketones exist in much smaller amounts all around us. If you do any cooking, you probably take advantage of several common aldehydes, like benzaldehyde, the compound that makes almond extract, and therefore the Dutch treat banquet so tasty. It's present in most stone fruits to some extent, so some people characterize it as having a cherry scent. Or you might enjoy some vanillin, the aldehyde that makes vanilla so tasty, or maybe even cinnamaldehyde, which makes cinnamony. Ketones are important kitchen compounds too, from the 2-heptanone that is in clove oil and pumpkin flavorings, to the butadiene that's used for artificial butter flavor, or the carvone that gives us characteristic spearmint taste. Carvone is a fun molecule because they're actually 2 stereoisomers. If you don't remember, that's a type of isomer that's only different based on the directions that things are bound in space. So the other form flips the bottom 3 carbons to the other side of the ring. On the left it's shown pointed back, and on the right it's shown pointed forward. And that simple flip changes the taste from spearmint to caraway seed, which is probably most recognizable to most of you in rye bread. Ketones are also one of the functional groups on many steroid molecules. Steroids are molecules that share a common core structure shown on top and are important in many different roles biologically. Many steroids are messenger molecules and have regulatory roles in the body. 3 examples are shown: testosterone, progesterone, and cortisone. Notice that each of them end in -one based on the ketone. These steroids are really complicated to produce from scratch, but are also really important drug targets. Progesterone is used in birth control, and cortisone is used to treat arthritis. Some of the first viable drug treatments were made available by Percy Julian, a Chicago chemist who developed syntheses of steroid molecules from Mexican yams and soybeans, which drastically dropped the price and allowed steroid molecules to be used as treatments for common folks. There's actually a Percy Julian High School about a mile east of my house.